Swayam Prabha. Digital India. Educated India.
Hello everybody. Today we are going to continue with performing material balance calculations for single unit processes without reactions. We have already looked at many processes. We will continue looking at some of the more common processes in chemical and biochemical industries and try to perform material balance calculations on these processes. The next process we are going to look at is distillation. A distillation is a process which tries to separate two liquids based on their difference in boiling points. The distillate which comes out contains the more volatile components, and you have the bottoms which contains the less volatile components. The separation is done by boiling. The difference in the boiling point of these materials which are entering is used as the way to separate these two. We need to understand that perfect separation is not possible in distillation. You end up getting a mixture in both the distillate and the bottoms. The accomplishment which you will look for is to get a purer form in your distillate. Here is an example problem which we shall try to solve today. Hard liquor is produced by distillation of liquid drinks made with grains, fruits or vegetables that have already gone through alcoholic fermentation. To increase the alcohol content, the fermentation product containing 5% ethanol and 95% water by mass is fed to a distillation column. A product stream leaving the top of the column contains 20 mole percent ethanol, and the bottom product stream contains 5% of the ethanol fed to the column. The flow rate of the feed stream is 2000 kilograms per hour. Determine the mass flow rate of the overhead product stream and the mass flow rate and the composition of the bottoms product. So now we have been given a lot of information. We need to find the basis and draw the flow chart to describe the process. So here I want you to look at the problem statement carefully. So there is one flow rate which has been given, which we can use as the basis. So the flow rate of feed entering into the distillation column is given as 2000 kilograms per hour. So that would be the basis for our calculations. Based on the flow rates given in the problem, we can identify that the basis for this problem would be 2000 kilograms per hour. So that is the flow rate of the feed stream entering into the system. So we will say that basis is 2000 kilograms per hour. And now let us try and draw the flow chart to describe the process. We have a distillation column which has one feed and two output streams. So the feed stream has been told that the flow rate is 2000 kilograms per hour and contains 5% ethanol and 95% water. So it has been clearly stated that these percentages represent the mass percentages. Conventionally, liquid and solid streams would be expressed in terms of mass fractions and mass percentages, whereas gases are usually represented in terms of mole fractions. That is why you would see that the distillate stream which would contain the volatiles has been given as 20 mole percentage ethanol. So this convention is followed because measuring the volume of gases is a lot simpler and measuring the masses of solids and liquids is easier. So when you measure volume for a gas, it can be easily converted to mole percentages under ideal gas conditions. So using mole percentages or volume percentages are more common for gases. So here it has been told that the distillate stream contains 20 mole percent ethanol and the bottom stream contains 5% of ethanol fed. So you need to be careful. You need to understand that the problem statement clearly says 5% of the ethanol which is entering the system leaves through the bottoms. This 5% does not represent a mass percentage or a mass fraction of the stream. So this has nothing to do with the composition of your bottom stream. It only says that 5% of ethanol which is entering into the distillation column leaves through the bottoms, which would mean the rest would be leaving through your distillate. So now if you look at this problem, we have one issue. When we discuss the fundamentals for solving material balance problems, one thing which I told you was to convert all the values given to either masses or to moles. Here your feed stream is given in terms of mass fractions and your distillate stream is given in terms of mole fractions. So to avoid confusion, we need to convert one of these to the other so that calculations become easier. In this case, I have chosen to convert the mole percentage of the distillate into mass percentage. How do we go about doing this? We have already seen an example problem. Why don't you pause this video and try to continue with that calculation so that you can get the actual mass percentage of the distillate. Now that you would have completed it, please have a look at how I get it and confirm if your answers are correct. To convert the 20 mole percent ethanol into mass percentage, we first need to assume a basis of 100 moles of distillate stream which is leaving the system. So we will start with a basis for this conversion alone as 100 moles of distillate. And as we did in the example problem in the earlier class, we will build a table which will help us to convert these mole percentages to mass percentages. So the table would contain ethanol and you would have So the table would contain the components which are ethanol and water, and you would have to write down the number of moles of each, the molecular weight of these streams and the mass of these components, and finally you will be able to calculate the mass percentage. So the moles have been given as 20 mole percent and 80 mole percent for ethanol and water. Assuming the basis of 100 moles of distillate, we know that 20 moles of ethanol and 80 moles of water would be present in this 100 mole distillate. The molecular weight for ethanol is 46.1 grams per mole and the molecular weight of water is 18 grams per mole. So using the molecular weight, we can convert the moles to masses by multiplying moles times molecular weight. This gives us the mass of 922 grams of ethanol and 1440 grams of water. So this can be added to find the total, and dividing the mass of ethanol divided by the total of these two masses would be 922 divided by 1440 plus 922. This times 100 will give you the mass percentage of ethanol, and similarly 1440 divided by 1440 plus 922 times 100 will give you the mass percentage of water. So this is calculated to be 39.03% and 60.97%. Now that we have converted these values to mass percentages, let us move on to solving the material balance problem. So this flow chart gives you all the information that has been obtained from the problem and all the information that we have just calculated. Now, so the problem statement clearly states that 5% of ethanol entering the system is actually leaving through the bottoms. So we also know that 5% is the mass fraction of ethanol in the feed stream. So we can calculate the amount of ethanol entering into the system as ethanol input is equal to 5% of 2000 kilograms, which is 100 kilograms per hour. Out of this, 5% leaves through the bottoms. So ethanol in bottoms would be equal to 5% of this 100 kilograms entering, which is basically 5 kilograms per hour leaving through the bottom stream. Now that we have calculated all the information from the problem, let us perform the total and component balances for this system. What would be the total balance for the system? The total balance is given as input equals output. So, input here is F or the feed, which is equal to the sum of the distillate and the bottoms, giving you 2000 kilograms is equal to D kilograms per hour plus B kilograms per hour. We can also write a component balance for ethanol, and that would look like this. Again, input equals output, and input for ethanol is 0.05 times F equals 0.3903 times D plus 5. So, from here we can calculate D as 256.2 kilograms per hour. So, the distillate which is leaving the system is equal to 256.2 kilograms per hour. Substituting this back into the total balance equation, we can calculate the bottom stream to be B equals 2000 minus 256.2 kilograms per hour, which is 1743.8 kilograms per hour. So, now we have the information about the mass flow rates of the bottom stream and the mass flow rate of the distillate. We need to calculate the composition of the bottom stream so that all the information that is required from the problem is complete. To calculate the mass fraction of the bottom stream, we have the information about the mass of ethanol leaving the system through the bottoms and the total mass of the bottom stream. So, the mass fraction of ethanol in the bottom stream would be, let us call it as X ethanol in bottoms as 5 divided by 1743.8, and the rest would be the concentration of water, which would be 1 minus 5 divided by 1743.8. So, these values are 0.00287 kilograms per kilogram and 0.99713 kilograms per kilogram. With this, we have calculated all the parameters that need to be measured for defining this process. Let us move on to the next process, which is a partial condenser. For a partial condenser, you have a vapor feed which is fed to the condenser. Some of the vapor feed is condensed to form the condensed liquid and leaves through the bottom of the column, and the rest leaves as the vapor product. So, the feed actually would contain condensable vapor components and non-condensable components also. The exit stream is always in equilibrium. So, that is why you have a vapor product and the condensed liquid leaving from the system. So, this process is usually done through cooling or by increasing the pressure. You also have a process called flash vaporization or flash distillation. So, here what happens is a liquid feed is fed to the flash unit and you have a vapor product and a liquid product leaving the system. This is similar to the partial condenser, except that the feed here is a liquid instead of the vapor, which would be the case in partial condenser. Vaporization here is done by reducing the pressure or by heating. The vapor liquid streams are in equilibrium and they exit the system at equilibrium conditions. You also have a gas dryer. So, the earlier dryer which we looked at was a direct dryer where heat was directly supplied to the system. Instead, in a gas dryer you have a feed gas which enters into the system, and you also have a dryer feed which needs to be dried entering into the system. So, the volatile components in the dryer feed are evaporated and they enter into the feed gas and leave as exit gas, and you get the dried product through the other side. So, the solvent is transferred from the dryer feed to the feed gas. This process can actually be split into two units. The first unit would be the direct dryer, and the next would be the mixer for the feed gas and the solvent. So, in case of a direct dryer, what you would have done is you would have the dryer feed and the dryer product, and heat being supplied where the solvent exits the stream in vapor phase. So, the next step could be the vapor phase solvent getting mixed with the feed gas and leaving as the exit gas. So, that is why this single process can actually be divided into two processes for your analysis. Here is another common system which is used in many chemical and biochemical industry. It is called a crystallizer. A crystallizer feed enters into a crystallizer and you end up getting a slurry product which leaves the system. So, what happens here is solid crystals are produced from the crystallizer feed by change in temperature. So, this flow sheet many a times would include a filter also, because the crystals which are produced need to be separated from the liquid which is accompanying in the slurry. So, for this reason you would have a filter attached to this, remove the solids from the slurry, and the liquids will be sent out as the filtrate. Here is an example problem for a crystallization process. A tank holds 10,000 kilograms of a saturated solution of Na2CO3 at 30 degrees Celsius. You want to crystallize from this solution 3000 kilograms of Na2CO3 10H2O without any accompanying water. To what temperature must the system be cooled? Now, until this point, every material balance problem that we have performed has always asked us to calculate mass flow rates or mass fractions or molar flow rates or mole fractions. Here the problem statement asks us to calculate temperature. So, that is the reason we are given with additional data, which is the solubility of Na2CO3 in water. If you look at this data, it shows the dependence of the solubility of Na2CO3 with respect to temperature. You have been given solubility in the terms of grams of Na2CO3 per 100 grams of water. You need to carefully understand that these units are grams of solute per 100 grams of water. When you are using these values, you should appropriately use the correct units, thereby eliminating any errors. Okay? Now, let us move on to see how we go about solving this problem and how do we arrive at the temperature finally. As with every other material balance problem, the first step for this problem would also be to identify the basis. Here we have been clearly told that the tank capacity is 10,000 kilograms of saturated solution. So, we will go with 10,000 kilograms as the basis. So, we write down the basis as 10,000 kilograms of saturated solution. Now, we need to identify the flow chart which will describe this process. So, we have a crystallizer and we have one feed which is the saturated solution entering as 10,000 kilograms of saturated solution, and we have two different streams which will come out. So, the problem says that we will have 3000 kilograms of Na2CO3 10H2O leaving the system, and the rest will be leaving in the form of the solutions. So, this would be a saturated solution which we do not know the mass. So, we will call it M2, M2 kilograms of saturated solution at T degrees Celsius. As we do not know the temperature, we need to finally calculate what this T is. So, now we have the flow chart. Let us see if we can solve this problem. So, the solid crystals which are leaving the crystallizer are actually not just Na2CO3. They contain the water of hydration, which is the 10 H2O molecules which are attached with every molecule of Na2CO3. So, now we need to calculate what is the mass fraction of Na2CO3 in the 3000 kilograms which is leaving in the form of crystals. So, for that we need to understand the molecular weight of Na2CO3 and the molecular weight of 10H2O and use that for calculating the mass fractions. So, 1 mole of the crystal contains 1 mole of Na2CO3 and 10 moles of water. So, the mass fraction can be calculated using the molecular weights. So, 1 mole of Na2CO3 technically contains 106 grams of Na2CO3 and 180 grams of water. So, the 1 mole of the crystal So, now that we have calculated now that we have drawn the flow chart and identified the basis, let us look at solving this problem. So, there are a few things which we need to understand clearly. So, we have been told that 10,000 kilograms of saturated solution of Na2CO3 is entering the crystallizer. First, we need to know what is the mass fraction of Na2CO3 in the saturated solution. For this, we can use the solubility data. So, the solubility data tells us that 38.8 grams of Na2CO3 can be dissolved per 100 grams of water. So, at 30 degrees Celsius, the saturation data is 38.8 grams of Na2CO3 in 100 grams of water will give you a saturated solution. This is at 30 degrees Celsius. This means the mass fraction of Na2CO3 can be given as 38.8 grams divided by the total mass of the solution, which is 38.8 plus 100, giving you 38.8 divided by 138.8, which is 0.280 grams per gram. So, mass fraction of water in the solution entering would be 1 minus 0.280, giving you 0.720 grams per gram. So, this means we have 2800 kilograms of Na2CO3 and 7200 kilograms of water entering the system. So, the next step is to identify the mass fraction of Na2CO3 in your exit streams. The first exit stream is the crystal. Although this is only the solids, this also contains water, which is the water of hydration. You can see that every mole of Na2CO3 is accompanied by 10 moles of water to form the crystals. So, 1 mole of crystal basically contains 1 mole of Na2CO3 and 10 moles of water. So, we can calculate the mass fraction of Na2CO3 using this system. 1 mole of crystal contains 1 mole of Na2CO3 plus 10 moles of water, which is 106 grams of Na2CO3 and 180 grams of water. So, this implies 286 grams of crystals will contain 106 grams of Na2CO3 and 180 grams of water. So, mass fraction of Na2CO3 in the crystals would be equal to 106 divided by 286, which is 0.371. Similarly, mass fraction of water in the crystals would be 180 divided by 286 or 1 minus 0.371, giving you a value of 0.629. So, now that we have all the information about the mass fractions, let us go ahead and perform the balance equations. So, let me just fill this table so that we have all the information which we calculated. So, we had calculated that the mass of Na2CO3 entering in through the solution is 2800 kilograms and water is 7200 kilograms, and we have calculated the mass fractions for these Na2CO3 and water here as 0.371 Na2CO3 and 0.629 water. So, if we were to write a balance equation, we can start with the total balance, which would be 10,000 kilograms of feed entering would be equal to 3,000 kilograms leaving as crystals plus M2. So, M2 will be equal to 7,000 kilograms. So, the next step is to perform a component balance. Na2CO3 balance can be written as follows. So, you have 0.28 times 10,000 which is entering, which is 2800, and you have 0.371 times 3000 as the mass of Na2CO3 leaving through the crystals, plus an unknown concentration of Na2CO3 in the saturated solution leaving, which will be called as X, times 7000, which is the mass of the saturated solution. Now, using this equation, we can calculate the mass fraction of Na2CO3 which is leaving along with the saturated solution. So, this value can be calculated as X equals 0.241. So, based on this, mass of Na2CO3 in the saturated solution leaving is equal to 0.241 times 7000, which gives you a value of 1687 kilograms. So, water in the same stream would be equal to 7000 minus 1687, which is 5313 kilograms. So, now that we have these values, we can calculate what would be the solubility here. Now that we have calculated the mass of Na2CO3 and the mass of H2O leaving through the saturated solution, we can calculate the solubility data for this particular stream. When we look at the solubility table which was given, we knew that the units which were used was grams of Na2CO3 per 100 grams of water. So, we need to calculate the same units for this particular stream also. For this, what we will do is, we know that the mass of water which is leaving is 5313 and the mass of Na2CO3 which is leaving is 1687. So, these are given as kilograms of Na2CO3 per kilogram of water. Now, first thing we need to do is convert these kilograms into grams. So that we can do by 1 kilogram of water divided by 1000 grams of water times 1000 grams of Na2CO3, 1000 grams of Na2CO3 divided by 1 kilogram of Na2CO3. By doing this, we would get the values of solubility in terms of grams of Na2CO3 per gram of water. So that value would be 0.318 grams of Na2CO3 per gram of water. As we needed to calculate the amount of Na2CO3 dissolved in 100 grams of water, multiplying this with 100 would give you 31.8 grams of Na2CO3 dissolved in 100 grams of water. So this would be the solubility data which we will use to fit in the curve we can generate through the data provided. So if you look at this curve, this is the solubility data plotted against temperature. So we had the values for temperature and we plotted it using Excel, and the curve which we obtained was fitted for an exponential curve. So the equation which fits this curve has a very nice R squared value also. The equation is y equals 7.0115 e power 0.0568x, where y is the solubility and x is the temperature. So now we can actually plug in the value for solubility that we calculated, which was 31.8, and we can try to calculate the temperature from this equation. So what we do for that is, the equation is written down as solubility equals 7.0115 times e power 0.0568 T, where T is the temperature. So we calculated the solubility for the exit stream as 31.8 grams of Na2CO3 per 100 grams of water. So that needs to be used. So taking a logarithm on both sides, we can actually get ln of solubility equals ln of 7.0115 plus 0.0568 T. Substituting the value for solubility here, we can calculate the temperature to be 26.6 degrees Celsius. By cooling the temperature of the stream entering at 30 degrees Celsius to 26.6 degrees Celsius, we can actually crystallize 3000 kilograms of Na2CO3 10H2O crystals. So with that, we will conclude the lectures for today. I hope you have understood the principles of distillation and crystallizer. So in tomorrow's lecture, we will talk about filtration, which is an important process in any downstream operation, and we will discuss the fundamentals associated with that and how to perform material balances for a filtration process. Thank you.